Hello, and welcome to today's plenary session. My name is Tamsin Mather, and my co-chair, Liz Griffiths. We are the co-chairs of the Science Committee for this year, and it is our absolute pleasure to introduce today's plenary speaker, Dr. Ellen Stofan of the Smithsonian Institute. As Under-Secretary for Science and Research, Dr. Stofan oversees the science museums, research centres, libraries and archives, and several other offices. Her focus is on the Smithsonian's Our Shared Future, Life on a Sustainable Planet initiative and collective research, especially in areas of biodiversity, climate change, global health, sustainable communities and environmental justice. She was previously director of the Smithsonian's National Air and Space Museum in Washington, D.C., and as the former chief scientist of NASA, Dr. Stofan served as the principal advisor to the administrator on science programs and strategic planning. She is currently on the science team of the NASA Dragonfly mission to Titan and joins us today by live link for reasons that she will explain shortly. Welcome, Ellen. A pleasure to have you with us.
Thank you, Tamsin, so much, and thank you all of you, and especially to the Science Committee for inviting me to speak today. I am very sorry I cannot be there today due to overzealous skiing back this spring. I messed up my knee, and I am recovering from knee surgery, so I am very sorry not to be there, but my walking isn't totally recovered. I'm going to go ahead and share my screen, and after all this time, we should be able to do this quickly. There we go. I'd like to talk today a little bit about a lot of the work that we do at the Smithsonian, but sort of something that I think about a lot. Several years ago, I participated in an Oxford Union debate, which my team actually did lose, on the question of whether the future of humanity is in space. Now, you might think, given my background, that I argued that the future of humanity was in space because of settlements on other planets and moving humanity beyond and off Earth. But that was actually not the approach that we argued at all. And what we argued is what I'm going to be talking about today, that it's not about moving humanity off Earth. It's using space, our assets in space, to look back at our home planet to try to help save it from ourselves. I think as long as humanity has looked up at the night sky, whether you were an artist or a philosopher or a scientist, you ask the question, are we alone? Is humanity have any companions out there in our solar system, in the universe? It's astonishing to me that now we are actually on the cusp of being able to answer that question. But even as we do, we constantly have to hearken back to the fact, and I go back to Carl Sagan's words on this because he said it way better than anybody else has, that on this pale blue dot, there really is nothing out there to save us. And we have to put our efforts, our technology towards sustaining life here on planet Earth. As Tamsin said, I'm now the Undersecretary for Science and Research at the Smithsonian. And I think when many people think of the Smithsonian, they think of our 18 museums on the Mall, the Ruby Slippers, the Apollo Command Module, and maybe even the National Zoo. But for those who know the Smithsonian well, they know that we were actually founded as a research institution about 177 years ago, that we have over 800 scientists. We have the largest natural history collection in the world. We have the longest studied tropical rainforest in Panama, down on Barrow, Colorado Island at the Smithsonian Tropical Research Institute. We study threatened coastal ecosystems, both at STRI and at the Smithsonian Environmental Research Center. We are imaging black holes and building an instrument to detect elemental oxygen in the atmospheres of planets around other stars for the Giant Magellan Telescope at the Smithsonian Astrophysical Observatory. And we have one of the largest forest networks in the world. And yes, we also help save species, including helping move our beloved pandas from endangered status to threatened. So the Smithsonian is all this and more. You know, when I came to the Smithsonian, I was mostly familiar with the research that we did that was related to the work I did. Since I'm a planetary geologist, I study volcanoes across the solar system. And obviously I knew of the work the Smithsonian did at the Global Volcanism Project. I knew of the work of people like Liz Cottrell, who study geochemistry to help us understand the evolution of this planet. And we have a number of scientists who do what I do, who study planetary science. So whether it's Jenny Whitten at the Air and Space Museum, using flows in Iceland as an analogy for flows on Venus for the Veritas mission, or whether it's the work we do in Hawaii as an analog for volcanoes on Mars and Earth. We do an awful lot of work both with our collections and in the field, trying to understand the evolution of this planet. But we also look, as I said, beyond Earth, out into the universe through our work at the Smithsonian Astrophysical Observatory. This is an image from our Chandra X-ray Observatory, a telescope that we operate in space for NASA. And it gets us back to that question of life. We know that the elements associated with life come from stars, and especially the explosions of stars, such as captured in this image of the supernova at Cassiopeia A. But what is important about this image and what the X-ray information is helping us understand is actually being able to see those elements. So whether it's the purple showing you iron or the green showing calcium, we know that the building blocks of life have been distributed not just in our solar system, but across the universe in energetic events like this. And we also know from satellites like the Transiting Exoplanet Survey Satellite or the Kepler Space Telescope that almost every star you see in the night sky has a planets around it, if not entire planetary systems. And I think that's one of the engaging things that we've certainly been seeing from TESS is how many multi-planet systems there are, and of course followed up on those analyses with the James Webb Space Telescope. So we know, again, that the elements, the building blocks of life, have been distributed throughout the universe, even by things like comets and asteroids bringing water to planets. And we now know how many planetary systems there are. In the future, even with ground-based telescopes like the Giant Magellan Telescope, we're building an instrument at SAO that's going to be able to detect elemental oxygen in the atmospheres of planets around other stars. Those planets probably identified with James Webb that we'll be able to follow up with the Giant Magellan Telescope. So this idea that we're getting closer and closer to not just identifying potentially habitable planets, but actually planets where we could start to try to understand, could they possibly be inhabited? But obviously that's beyond our solar system. And the question of whether life exists or has existed in the past in our own solar system is still an intriguing question. This is actually one of my favorite images that I actually comes originally from Dan Brownlee, but I got it from David Grinspoon, who some of you might know, because I especially love to show this to non-scientist audiences, not like you all, when I'm talking about habitable planets and how you find habitable planets and what a habitable planet actually means. Because for those of you who obviously understand the history of the Earth, you will understand these are actually all artist depictions of various stages in Earth's evolution, whether it was a magma ocean Earth, snowball Earth, our current Earth, or the future Earth. So this idea that habitability is not just a place, but it is a point or a duration in time in a planet's history is a complex one. And I know when most people think of these big telescopes, especially the planet finding telescopes that will launch in the future, they think about finding Earth 2.0, and they're thinking about that blue planet when they think about Earth 2.0. I personally am always most intrigued about the fact that we're actually at some point going to be able to study multiple magma ocean planets, which I find one of the most intriguing points in Earth's history. And some of you might be familiar with this concept that the astrobiology community uses, that, okay, now that you've determined that a planet is potentially habitable, when you send instruments there, what exactly is it that you're looking for? Are you looking for life as we know it? Maybe life that has functional molecules such as DNA or RNA? Though what we're far more likely to run across is life as we don't know it. And so how do you actually identify life if it is not sure what you're looking for? And this idea of this ladder of life, of what you're trying to look for, right now we're sort of hovering around that general indicators and potential biomolecule components. We're looking on the surface of Mars for functional molecules. But right now, what we've been finding are potential biomolecule components, which is exciting. We find fragments of organic molecules, but we don't know if they're indicative of biological or non-biological processes. Obviously, up to the point, and I really thought about this when I spent time designing a probe that would have landed in a methane sea on Saturn's moon Titan. How do you look for life with very basic instruments on another world, especially when that life might be life as we don't know it? In our own system, the places that we go to look for life, or that we think harbored past life, are numerous at this point. Venus up there in the upper left is intriguing. Obviously, on the surface of Venus right now, it's certainly too hot to accommodate life, especially anything that's related to water on the surface. There have been proposals that there could be life in Venus's clouds. I am still a skeptic. But nevertheless, we know that very early in Venus's history, it did have a lot of water, and it potentially had water on the surface, and therefore could have had life on its surface at some point in time. Similarly, Mars, which I'll come back to in a minute, Mars is certainly one of the more intriguing places in the solar system, and why NASA has spent so much time and energy exploring the surface of Mars, because we know that water not just existed, but persisted. And then, of course, when we're thinking about looking for life beyond our solar system, we're thinking at that planet level. But some of the most intriguing places to look at in our own solar system are actually satellites of other planets, basically the icy worlds of the outer solar system. So whether it's Enceladus or Europa, where we know there are substantial subsurface oceans, which are actually venting out into the atmosphere via vents, as you see the erupting one on Enceladus down at the bottom of the image, or the cracks on Europa near its south pole, where the Hubble Space Telescope has detected eruptions of liquid water from the interior. These are particularly intriguing places to go where there could be life in these subsurface oceans. And the center right image there is of Saturn's moon Titan. The glint you see at the top of the limb of the moon is actually light, specular reflection from the sea at one of the seas at the North Pole of Titan. And the idea that in these liquid bodies on Titan, you don't have water as a working fluid, but you actually do have liquid hydrocarbons. It's very cold, so chemical reactions proceed very slowly, but could you actually proceed towards something like life on Titan? And certainly that's one of the things that the Dragonfly team is thinking about. as later in the 2020s, we will launch the Dragonfly mission. It's an octocopter that will land in the equatorial region and study a number of features where we know there's been liquid on the surface in the past on Titan, and we'll go to an impact crater, and it's a particularly exciting mission. But Mars is definitely the place that we have spent the most time trying to understand past habitability. And, this image is one of my favorite for thinking about that, because these images of what are clearly interbedded sedimentary rocks, shales, sandstones, the kind of rocks that many of us who are familiar with terrestrial environments feel very comfortable looking at. And some of the more recent images that have come back from Mars have intriguing proof that water persisted again on the surface for a very long period of time, making it and understanding now from the chemistry of these rocks that the environment was potentially habitable in places on Mars, makes it, to me, even more imperative that at some point we do get actual geologists down on the surface of Mars cracking open lots and lots of these rocks, trying to find fossil evidence of life on Mars. So we understand that because these conditions didn't persist for an incredibly long period of time on Mars, that the long-term evidence of life is not going to be, there wasn't enough, I can't speak, there wasn't enough time for life to come into a more complex form on Mars. So we are looking probably for single-celled, multi-celled, very simple types of organisms, hard to see, hard to find. But I think if you look at the overall weight of science, we believe that it is the most likely place to go to understand whether or not life evolved beyond Earth and our solar system. And why does that matter? I think it matters because when we start looking outward beyond our solar system, understanding that there were potentially multiple origins of life within our own solar system is incredibly important. And based on the science, based on what we know about how rapidly life evolved here on Earth once conditions stabilized, I personally strongly feel that we will find evidence of past life on Mars on at least one of the icy satellites of the outer solar system, which will again then make us more inclined to think that there could be life beyond our solar system. Which I think on some level brings us back to this planet and really thinking about the crises that we are facing at this point in time. Because as we've understood from looking at the history of our own planet and from the history of the planets across our solar system, habitability, even under the best of conditions, is potentially fleeting. And our own planet is no exception to that. And we also understand that due to human activity, life on this planet is under great threat. So whether it's human expansion into ecosystems, whether it's pollution, or whether it's the effect of climate change, right now we are probably experiencing the sixth mass extinction. We understand right now that we use more, our ecological footprint of the world is more than we should be using every year and ever increasing. We see the clear effects of climate change, whether it's the incredible wildfires that we experience, certainly in Washington, D.C., where I live. I can tell you last year, walking out my front door and smelling what I thought could have been a bonfire around the corner and finding out it was a wildfire in Quebec, and not being able to see more than 50 yards in front of me from the smoke that was coming down from Canada into the east coast of the United States was fairly astonishing. Or whether it's the incredibly warm sea surface temperatures that we've been seeing over the last about 16 to 18 months. These effects of climate change are affecting our planet right now. We're seeing them. and it's pretty daunting. And I would say it's easy, certainly for me, and certainly I think for many of us, to feel overwhelmed by this and to feel like we're in a bad position that we don't see a way out of. But one of the things that I think I have been able to focus on is the amazing amount of work we are doing as scientists, as a scientific community, to understand how to become more resilient to the effects of climate change and how to better predict and understand what's happening on the planet and find solutions. So I want to share with you some of the work that we're doing across the Smithsonian, using both our collections, using space data, using the research that we do across the surface of this planet to help come up with solutions around climate, especially solutions around where nature and climate come together. At the Natural History Museum and our Smithsonian Environmental Research Center, we have a collaboration that I think is really amazing, because looking at the spacing of veins on ginkgo leaves, and for those of you who love trees, you'll know that ginkgos have been around for millions and millions of years, that the spacing of the veins on the ginkgo leaves is related to the concentration of carbon dioxide in the atmosphere. So we're doing an experiment where we're growing ginkgo trees in controlled greenhouses where we alter the amount of CO2 and measure the spacing of the veins and comparing that to fossil ginkgo leaves in our collections to better help us understand how to use fossils to constrain past climate in order to improve climate modeling. We're doing a similar thing with pollen, looking at pollen from fossil assemblages from times like the Paleocene-Eocene thermal maximum from various ecosystems by using artificial intelligence to identify huge numbers of pollen grains. It helps us to better constrain what was living in these ecosystems in time, allowing us to much better constrain likely temperature and rainfall profiles, which can then be tied back to past climate modeling to help improve the forward modeling of climate models. So the idea that we can take everything from a fossil leaf to assemblages of pollen grains and improve future climate modeling is pretty exciting, especially when we do something like apply artificial intelligence. At the Smithsonian, we're also putting satellites and instruments in orbit in order to better understand what's happening with our atmosphere. We're taking the same technologies we use to study beyond Earth and turning them back to this planet. So whether it's the methane air instrument that we built is for the precursor to the Environmental Defense Fund's methane sat, and we're currently helping process and analyze that data to understand better and identify sources of methane to help better constrain or help better police controlling the release of methane into the atmosphere. Or whether it's NASA and the Smithsonian Astrophysical Observatory's TEMPO instrument, which now measures air pollution, the key components of air pollution over North America hourly at pretty high resolution. For example, across the Washington, D.C. area, there's over 30 pixels. So you're getting neighborhood scale pollution, not just broad scale or single day measurements, which is what we had before we launched TEMPO about a year and a half ago. These data are incredibly important for helping us better track pollution data, but they're also really critical data for helping us address issues around environmental justice. We all know that the areas that are the most polluted, this has been shown by numerous pieces of research, the areas that are most polluted are the ones where the most vulnerable populations are living. And so being able to have high quality data in order to assess environmental injustice, we hope to move towards better justice in the future. We're also using our data to help understand how to better constrain carbon. The way I like to think about it is, imagine if we still didn't agree how much a pound was or how long a mile was. It would be really hard for us to move forward with any kind of system. This is actually kind of where we are right now, with people out there trying to price carbon for various nature-based solutions. So if you can't agree on how much carbon is actually being sequestered, if you can't agree how to measure it, how to have the accuracy of it determined, you're really not going to be able to have something like a reliable carbon market if people don't trust and aren't open and transparent about how that system, what it is actually based on. And right now, that is certainly happening. In fact, all the products that are being derived using space-based data, using Earth observation, there's lots of products that are being put forward. But all of the space agencies have said that there's no current standard ground observations to verify and validate in an open way what these data mean. So with the help of the Bezos Earth Fund, we are actually working on this. The Smithsonian, as I mentioned earlier, helps to operate the largest network of forests around the world called Forest Geo. These are plots around the world that are a minimum of 25 hectares, where on a regular basis, we measure every stem, yes, every stem, that is growing in these forest plots. While we've been doing this for over 30 years to help us understand how forests grow, how they evolve over time, over the decades, this forest network has become a powerful measure of the effects of climate change, of changing temperature, changing precipitation on forests across the globe. By combining our network with other forest networks, we've formed a new forest network called GeoTrees, where we are combining ground laser data, drone-based laser data, and space-based data to precisely constrain how much carbon is tied up in reference forests in the tropics and we're doing this in an open and transparent way so that tropical carbon can actually be verified for anyone who's trying to say, all right, we're going to do a carbon market based on this. This is now open source, validated, transparent data that can be based on. We want to expand this to forests across the world, not just in the tropics, but we're beginning in the tropics. Again, I think these data are critical in order to move us to a carbon-based trading system that's actually based on science and not on, let's just say, snake oil. We are working to do the same thing with lots of partners. And again, I have to, hugely shout out our partners on GeoTrees, its forest networks around the world, as well as the major space agencies. We're doing the same thing with partners for blue carbon, marshes, mangroves, swamps. Through our Coastal Carbon Atlas, through the experiments we do, we actually have the longest running CO2 experiment on a marsh in Maryland, where we measure carbon. To take our understanding of the growth and the importance of these coastal ecosystems in storing carbon over time, understanding their tipping points, because we know from some of the experiments we've done and others have done that you heat up, for example, marshes too much, they go from being carbon sinks to carbon sources. So that's something that has to be carefully monitored and managed. To helping countries measure, like we have in Belize, the amount of carbon that's being stored in their mangroves for part of their nationally determined contributions under the Paris Accords, but also to help them understand the importance of preserving these ecosystems, which aren't only important for for the carbon they sequester, but of course the fact that they are necessary for fisheries, they're necessary for clean water, they're necessary for preserving birds and other species. And so these ecosystems, whether they're forests on land, whether they're mangrove forests, these are critical ecosystems whose impacts go way beyond the carbon measures, but are important also for that. As the conversation has moved from understanding and trying to quantify carbon as part of nature-based solutions, increasingly conversations have turned to going beyond just carbon to measuring biodiversity and putting a value on biodiversity in order to help people understand how to protect it. But in order to understand or measure or quantify nature, you have to understand not just where it is, but where it is when, because obviously species don't stay in one place, they move. And so whether it's tracking giraffe and wildebeest in Africa or tracking birds as they move across the globe, you need to know where species are. And this is again where satellite data and tracking data become incredibly important to understand species, where they're going, where they are, because then you can start worrying about how to better protect them. We are doing this out in Montana, where we are working with tribal communities using tracking data to understand the movement of bison on their lands with several tribal nations in central Montana. The bison are critical ecosystem engineers in that area. When you put bison back on land, it restores the prairie grass ecosystem, which brings back birds, it brings back insects. So when you have ecosystem engineers put back on land like this, we've also been restoring black-footed ferrets and swift fox into these ecosystems. And you can actually see the prairie ecosystem, which has basically not existed in a vital way in that area for over 100 years. You see that ecosystem coming back. So it is possible to go into these areas where humans have altered the land, how it's used, and by understanding and measuring and monitoring, you can actually start to have an effect for restoration in these areas. We're doing the same thing, working with Maasai-based conservancies in Kenya, where we're combining satellite data, high-resolution satellite images with artificial intelligence to track the movement of wildlife across these ecosystems. This is incredibly important for understanding how to work with people, for example, on where they're going to put roads and fences on property to understand how to best allow the wildlife to move through the ecosystem as food availability changes from region to region seasonably and with rainfall patterns, especially as rainfall patterns have been changing at a rapid rate. And it allows us to understand how to reduce human-wildlife conflict. So this combination of using space-based data with artificial intelligence to help speed up identification of species and understand their and predict their movements is critical. But we don't have to just understand where the species are. We have to also understand where the humans are and what they're doing to reduce human-wildlife conflict. So we're also using artificial intelligence to help us identify bomas, which are where cattle are kept at night, combining that with land monitoring of where elephants are moving, where lions are moving. It can again reduce human-wildlife conflict to allow the ecosystem to be preserved as much as possible while allowing humans to have economic benefit from the areas that they live in. We're also in these regions looking at conflict between humans, wildlife, and livestock that comes in not through direct conflict, but through transfer of disease. So understanding again how these wildlife are moving, where they're getting water from, where they're sharing water with livestock is incredibly important for understanding zoonotic disease transfer. So I've been spending some time talking about how the Smithsonian is helping us understand how to use space-based data, not just to understand the origins of life and where else it could be in the solar system, but also you turning that satellite data back to Earth to help us understand how to make life on this planet more sustainable. But our role as the Smithsonian is also to educate and to inspire. In 2019, we were celebrating the 50th anniversary of the Apollo landing on the moon. And we were able to bring over 1 million people to the National Mall to celebrate that moment for 6 days across July by launching a Saturn V rocket up the side of the Washington Monument. It's hard to see there, but that Saturn V is actually projected on the side of the Washington Monument, reminding people that when humanity puts its mind to doing something, it can actually accomplish amazing things. Going from the original call by John F. Kennedy in 1961, when at Rice University, he talked about why we went to the moon, not because it was easy, but because it was hard. And what we had to invent at that point, we didn't have spacesuits. We didn't know how to do spacewalks. We didn't know how to navigate to the moon. And yet 9 years from that speech, we landed humans on the moon. So this idea that when we're facing huge challenges, like the biodiversity crisis, like climate change, we are capable as humanity of stepping up and addressing these crises. And so using this moment of Apollo to remind people, look what we can accomplish when we actually put our mind to it. If you miss this and you want to see it, it's on YouTube. It's called Go for the Moon, and I urge you to watch it. We also use our museums, whether it's the National Air and Space Museum, whether it's the National Museum of Natural History. We use our museums to try to educate the public about science, to understand what we do as scientists, the information that we gather, to understand the planet that they live on, how the planet works, and how they can use this information and how we are using this information to help better understand our planet. So whether it's the Deep Time exhibit at the Natural History Museum, where we talk about the effects of climate change on the planet currently, or whether it's the gallery that you see in the lower right that will open at the Air and Space Museum in about 1.5 years on the Mall, where we're going to talk about how it has been through the use of aircraft and satellite data that we've been able to understand that climate change is happening, but also how those particular industries are changing and modifying to reduce the impacts of climate change on the planet. What we know from studies is that telling everyone what's wrong, explaining how scary climate change is, like I did on a number of slides ago, those are things we all know, right? We understand that we're in the middle of a biodiversity crisis. We understand that the oceans are warming at a frightening rate and that we're losing a huge amount of ice every year, especially in the Arctic. We need to make sure the public understands that, but we know that doesn't motivate them to action. What motivates people to action is by giving them hope, giving them solutions, letting them understand that by using science, by using data, we can find pathways to make ecosystems more resilient, to bring species back, to use the knowledge that we have to create a better future. So these are the stories that we try to tell across our galleries through the Smithsonian, are stories of solutions, stories of hope, and stories of possibility. The other thing that over the last several years that we've really worked on is how to make sure that the stories we tell are the stories of all of our population, not just some of our population. So whether it's talking about Bessie Coleman in the top center of the screen, Bessie Coleman was the first African-American woman to get a pilot's license. She had to go to France to do it because at that point, flight schools in the early 1900s in the United States, they didn't just not train women, they didn't train any African Americans. And yet she went to France, got her pilot's license, and came back to the United States and refused to fly at segregated air shows and would only fly if everyone could see her fly. Whether it's her story, whether it's the story of the Tuskegee Airmen helping to change the course of World War II, whether it's Ellen Ochoa, the first African-American, or sorry, the first Hispanic-American woman to fly in space, or Mae Jemison, or Katherine Johnson, or Amelia Earhart. There are people over the history of this country who have helped change the story, who have helped make significant contributions. And we have to tell these stories in order to ensure that we inspire the next generation to understand that they can be also part of the solution, part of helping make life on this planet sustainable. So thank you so much for having me here today, and I am happy to answer questions.
Ellen, thank you so much for an incredibly wide-ranging and inspirational talk. I'd like to invite anybody to ask questions. If you could remember, please, to come to the microphones. There's one either side in the aisles right here, so that Ellen is able to hear you. And while people are shifting around and thinking, formulating their question, perhaps I might start off with one, Ellen. You made many incredible examples of how technology enables us to see beyond ourselves, but also to look back in on ourselves and our planet, and that's been true forever, really. I mean, I think of the deep-sea telegraph cables enabling us to understand Krakatoa volcanic eruption in 1883 as a global event. What future technologies do you think are going to be key for us making the next steps in terms of pulling together as a species to solve these really big problems? Or what would you invent if you could wave your magic wand and invent anything?
Well, I think, one of the things that frustrates me is one of the things we critically have to do is decarbonize our economy. And we have the technologies to do that. And so I always get frustrated when people are like, we need to invent all these crazy, technologies to help us decarbonize the economy, when in reality we have those technologies at hand right now. And so I would say that we have many technologies in our hands to do this right now. What I'm really excited about from an ecosystem point of view, and also looking at the history of the Smithsonian point of view, we used to send people out if you think of the history of how we've tried to understand Earth, we've had people out in communities understanding what lives in their communities. We've had people who went around the world picking up shells or shooting birds and bringing their skins back to the museums of the global north to try to understand what lives on this planet, collecting fossils from around the planet to understand what has lived on this planet in the past. How do we've amassed these amazing natural history collections in museums across the world. And now we're applying cool technologies like the animal tracking I showed you, whether through satellite data or actually tagging animals. We're looking at environmental DNA or eDNA, where we're actually starting now in the Natural History Museum to collect samples of water that we are taking from oceans, from lakes, to track biodiversity, to understand and measuring biodiversity through DNA. We're also applying eDNA to land samples. We're hoping to collect in the coming years, bring formally into our collections, camera trap data, because now it's all about using technology is the new way of collecting a shell and bringing it back and putting it in the Smithsonian. But then when you think of the power of AI, and I know we're all like, please, not more on the power of AI, but if you think about what applying AI can do to the amazing sets of collections that we have in our museums, whether it's saying, I'm going to apply AI to digital images of every shell in our collection, plus add in DNA information where I have it, and let me try to then go back and ask questions about the evolution of mollusks on the planet, what we're going to be able to understand by applying new technology to old things like collections, I find extremely exciting.
Absolutely, and yeah, the collections are such a rich vein, so I'm really pleased to hear you mention that with the new technology too. We have a question from the floor.
Hello, this is a bit of a thank you and a question. Thank you first for a fantastic presentation today, and also thank you for being so generous with your time a couple of years ago to serve on a panel with our students at COP in Egypt at the US Center, and also to the Natural History Museum for helping us organize and host a workshop there for students, which was a year ago. And so my question is sort of to help the audience realize that these opportunities are available through the museums, and ask you to talk a little bit about how people can get involved or have students engaged in your educational activities there, because it was really fantastic. Your staff was just outstanding.
Thank you. Thank you so much. You know, I think a really strong role of the Smithsonian, and we're really leaning into this, is internships and fellowships at our institutions. In fact, the Smithsonian is starting a big fundraising campaign, as is every other organization in the world. But one of the things we're focused on is raising more money for paid internships. And our internships are generally at the college level, not the high school level. So these are for college students. We have so many interns who come to the Natural History Museum, who come to the Smithsonian Tropical Research Institute, to our Environmental Research Center, to SAO, to, I'm forgetting somewhere, I can never leave any of my children out, again, all of our science and research centers, because training the next generation, allowing them to use our collections, allowing them to access data like from the Event Horizon Telescope, or the tempo data, or the Coastal Carbon Atlas data we collect, bringing students in or interns in, and above all, making sure that those internships are paid so that we level the playing field and give every student the opportunity for engaging scientific research experiences where they can earn money across their internships is something the Smithsonian is deeply committed to. And so I really urge all of you to not forget that we have, like most organizations, like NASA does, we have a single entry point for internships, but they really do span pretty much the entire realm of the science I talked about today. And then at the postdoc level, because many of you certainly are training graduate students at the postdoc level, we are offering more and more fellowships every year, where we're focused again around life on a sustainable planet. How do we come up with solutions that help make life on this planet more sustainable? So whether it's carbon-based research that we're doing, whether it's how do we quantify marine biodiversity, whether it's working literally in the zoo with our animals, we have incredible opportunities for students. We're also, as you said, really leaning in on our role as a convener, and this is really important to the Natural History Museum, at the Environmental Research Center out in Maryland. We're really thinking about this. The Smithsonian needs to take a stronger role in bringing together scientists with policymakers, people from NGOs, to talk about these solutions, because they cross disciplines. We increasingly, as scientists, need to talk to these investment people who are coming up with things like green and blue bonds. We as the science community need to start talking more to the people in the economic community and the finance community, because they're running without us. And so we need to bring them in. So how we can use the Smithsonian as a platform to bring scientists in different communities together is something that we're really thinking about. And if people have ideas about that, come and talk to me.
Thank you very much, Ellen. We're beginning to push into lunch break, but if we had one more question from the floor. I think we're probably getting to the end of our time, so it just leaves it to me to thank you so much again, Ellen, for such an inspiring and wide-ranging talk, and for all the work that you're doing at the Smithsonian, which I've certainly learnt a lot about, and really look forward to learning more about. I'm going to go and look up about the projection of the Apollo rocket onto the Washington Memorial, which just looks completely amazing. So thank you very much again, and I hope you recover well from your surgery as well.
Thank you very much. Thank you for having me.